Tonight's lecture is given by Hamish Harvey. It gives me great pleasure to introduce you, Hamish, and I'm very grateful for you taking this on. Hamish currently runs Bill Harvey Associates and Obvious Limited, and many of you will know of Bill Harvey's work and of the Archie program and its diaspora. Hamish's background is as a civil engineer. He fought long and hard to avoid becoming an engineer, but finally gave in. A bridge engineer, that's right, yes, yes. He's had a lengthy spell modeling the hydrology of rivers and estuaries and things like that. But he started with Bill 10 years ago and has gradually enlarged his role until now, because of Bill's sad death 18 months ago, he's taken over the whole thing. So, and I'm delighted that when I challenged Hamish to do this, I suggested him he should investigate the history of people's theories about the behavior of masonry structures. And he's done that and turned it into his own thing, which is very much what I hope would happen, which is that his synopsis says an unsolved problem, the unsolved problem of masonry bridges. Now, we might have sorted out a bit about arches, but we really still know comparatively little about, or can say very little that's helpful about how bridges are going to behave. Well, we know how they behave, but we don't know what to do about it. Anyway, Hamish, please.
Thank you, Andrew. So it may seem odd, I suppose, that however long ago it was, a year ago, when Andrew asked if I could, my answer was, well, it's not actually a subject that I know that much about at this point. But that potted history of having really only started in 2010, it's a little more than 10 years, but not much with Bill. And obviously in that time, there's been a rather intensive apprenticeship building up into taking over more and more of the business. There wasn't much time in there for sitting, reading back into the history, and most of the time was spent working out what the current understanding was. Obviously, my background in bridges started before my time doing flood risk, because as Bill's son, we detoured many times on holidays to look at bridges. I also saw Bill, as we'll come back to, developing early Archie in the kitchen at home. So that was my introduction to computing as well in the early days of personal computing. Andrew has said that. I just want to say, just say, obviously the audience, I wasn't entirely sure what to expect. I am expecting there to be quite a wide mix. I have explicitly not aimed to teach anything to the established history group, who have quite a good grasp of a lot of this. But I hope there is in the audience some number of engineers working with or interested in masonry, but who aren't familiar with all the background. And that's really the core audience that I'm addressing. And there may be some non-engineers, in which case I hope there's enough non-technical content and photographs and interesting bits and pieces to keep that interest. Understanding is quite a strong word. Question is, how much do we really understand about bridges, as Andrew was saying? And what does that actually mean? Does it mean we've got tools that let us pour the numbers in and get an answer out? Or does it mean that by some mix of reasoning and calculation, we can achieve the confidence to build, the confidence not to build, the confidence to leave it as it is, the confidence to intervene and to decide what to do? Before we get on to theory, it's sort of obvious, but it's worth saying that an awful lot of bridges were built without anything like modern theory. And true arches, even quite sizable arches, are really very old. This is one of my holiday snaps that I took my son to just recently. The Chinese clearly had a very deep understanding of masonry behavior. I present this as representative of medieval bridges. Obviously, there are a lot of still extant medieval bridges. This is one of the more unusual ones with three abutments spanning a river and its tributary, Trinity Bridge in Culmann. And obviously, then there were waves of campaigns building, large numbers of bridges built to standard designs often. That's Bill's thumb. And even mid-1700s, William Edwards was being audacious attempt across the River Taff. His first attempt was a 3-span bridge, much like the one behind, or 3 or 4 spans, no longer known exactly, was washed away by a flood. But he'd been given a design, build, finance, operate contract to provide a crossing for 7 years. So he then thought, well, sod that, I'm going to cross it in 1 span. Saved from the flood. His first single span effort, second attempt overall, the centering collapsed before the bridge was complete. The centering had been built, I should say that Edwards was a country of wall builder, house builder. And the centering was built by his friend the wheelwright. It's just a big wheel. That collapsed for reasons we're not entirely sure about, maybe another flood, maybe just inadequate. The third attempt, second single span, the centering survived and was struck. The bridge was completed. It stayed up for a few weeks and then failed by the crown bursting upwards. At that point, Edwards was bankrupt, unsurprisingly. Fortunately, he was also the local minister, and the gentry had a whip round, put him back on his feet for his final attempt. There's some speculation that he consulted with Smeaton. There's no actual evidence of that. But the final bridge introduced these voids, tunnels through, possibly another one here, half tunnel, possibly some charcoal fill. You can see that the depth over the crown is in a sort of aesthetically odd thickening. And if you look from the top, the parapets are widened over the central section and narrow over the edge as well. More recently, in what I can only describe as being bold, the ground level on this side has been increased, and the level over the edge of the bridge was enhanced, which, given this bridge, is an interesting thing to do. But there's no theory going on here. It's all really rather extreme trial and error. Then obviously you have the canals, Telford's Highland roads, thousands of bridges, or about 1,000 bridges, and the railways, adding up to hundreds of thousands of spans. Built in sets, typically to standard designs, only very few of those pushing any kind of boundaries, and little, if any, use, even became all done to rules of thumb. Like ring thickness being the main thing. Lots of different takes on this. They all produce much of a muchness, very similar curves. That's all for a particular span to rise ratio. Those, I think, generally come from surveys of existing bridges. Obviously, this is the positive side of survivor bias. Surveying bridges that still exist is a pretty good way of deciding what works. That tends to come in more buttressing for vaults where you don't necessarily have soil behind. So the soil changes things there quite a lot. Okay, so through the development of theory, worth saying that I haven't really gone to primary sources very much, at least because French is a language that I never learned. And almost all theory happened in France. I'm drawing heavily on Heyman, who we'll meet later, and Huerta. In 1717, Goethe identifies 5 significant problems for the learned to resolve. 4 of those are related to masonry bridges. He wants to be able to establish abutment thickness, pier thickness as a proportion of span for multi-span bridges. How thick should the ring be at the crown? What shape should the arch be? And also retaining wall dimensions. That comes obviously a little bit after Robert Hooke, who famously, and this is the bit that almost everyone, I suspect, knows, published at the end of about something else entirely, helioscopes, an anagram with the letters sorted into alphabetical order for a Latin statement which he claimed showed the true mathematical and mechanical form for all manner of arches for building. As hangs the flexible line, so but inverted stands a rigid arch. That has been taken as a statement that the catenary is the shape of interest. So there's then a bit of pursuit of the mathematics of the catenary. 3 people found a solution. None of them publish a proof. Everything very close. There's lots of competition and people are worried about maintaining the proving that they'd got there first. In 1697, David Gregory published the whole thing with some errors apparently, but with a correct result. And he introduces a concept of infinitely small and rigid polished spheres sitting in an hanging in an arch. And he also already in 1697 makes this statement: when an arch of any other figure, any other shape than this perfect catenary, it's because it's in its thickness, some catenary is included, which is a sort of early echo of what turns out to be one of the really fundamental bases of arch stability. So he's recognizing that it will stand if some valid thrust line is present within it. But how relevant is the catenary really? Hooke didn't actually mention it. Many have ascribed beliefs to Hooke that aren't actually present in that statement. Did he really envisage a 1D continuum, uniform weight per unit length? Or would he have been thinking of a line of negligible weight with Boussois weights attached, as ultimately taken to a real extreme in practical application by Gaudi in 3 dimensions? So then 1695, Laïa, apologies for my French pronunciation, who in the process of his work on bridges invented a forced polygon and a funicular polygon, which is essentially the line of thrust of an arch. He initially assumed frictionless joints, so there's 0 friction joints between voussoirs, which means that the force has to be exactly perpendicular to the joint at every point in the arch. It also means that if you take your arch right round, if you have a semicircular arch and your springings are horizontal, you obviously have a horizontal force coming through from the arch, so you need an infinite vertical load to stop friction, to stop sliding in the absence of friction. He came back to it in 1712 and took completely the opposite approach of saying, you can assume that friction is actually enough that there will not be any sliding. So, and his object was to find thrust on the abutment. And this is the first introduction of the idea of, in mathematical terms anyway, the idea of the arch breaking at a particular point on this curve. A few years later, again, Couplay again starts with the 0 friction case, although he is aware and explicit about the fact that it's not of much interest. You can see him tracing the thrust and making sure that it's perpendicular to each section. And you can see that the voussoirs, if you like, have to get bigger and bigger as you come round to maintain that. And again, he comes back to it a bit later with a different approach. He states his assumptions: friction stops sliding, and there's no resistance to cracks opening, so no tension between, no tensile stress in the joints. And there's an unstated assumption that the stone won't crush. One of the things he looks at is the case of a weightless arch with a single central load. And he correctly establishes that it will be stable as long as the straight lines from the load point to the extrados at the springing stay within the masonry. And then he goes on to look at the minimum thickness for stability under the self-weight of the arch. And here he says he assumes a hinge at 45 degrees, but he correctly works out the maths for the thickness then. So the minimum thickness he comes up with is a little bit more than the true minimum, because the true hinge position isn't quite at 45 degrees, but the sensitivity to that position is not very high. So the error isn't very big. And then he goes on to look at abutment, thrust, and stability. Here he assumes that the thrust functions at the midpoint at both the crown and the springing. We calculate the horizontal thrust. I'm going to come back in a bit to the whole business of experiments and models, but this particular set are quite important because they influence the development of theory. Interesting. Danesi built really quite a large collection of physical models and recorded in great detail the behavior of them. Notice that here, for example, the failure is by rotation of the abutments. And that gets us to Culmann, which is the first pretty much complete understanding. In his essay note on the application of the rules of maximum and minimum to some problems of statics relevant to architect engineering. He covers strength of masonry piers, earth pressures, and dimensions of arches. And he is aware of that year's work. He doesn't seem to be aware of Coupley at all. He doesn't refer to Danesi's experiments, but he did know in Montpellier, so it's very likely that he knew about the results of those experiments, although they weren't published in a very obvious place. He, again, identified that friction is often large enough to preclude sliding. He assumed that tension in joints can be neglected. And he recognized, this is Coupley's diagram again, he recognized that this angle can't be assumed to be 45 degrees. You actually have to search for the worst case. And he identified that if an arch is stable, then the thrust must lie between some limits, and those limits will be calculated. I'm jumping now a bit. Thomas Young wrote an article for the supplement to the Britannica about bridges, and he includes in it the calculation of a line of thrust in the direction of curve of equilibrium for Waterloo Bridge. You note that it follows the center. He's fixing it at the center again at two positions, but it does show that it follows the curve well. At this point, we start sort of going backwards and forwards. So prior to this, all of that theoretical work was essentially theoretical. Bridges were being built by rules of thumb, trial and error, sometimes physical models. Now we start getting the interesting interaction, and the questions arise of what the particular engineer know at the point that they were designing a given bridge. John Rennie, New London Bridge, 150-foot span, how much calculation was involved in this? We don't know the answer to that question. Telford's bridge at Over. Telford had a lot of troubles with this, but that was all to do with the fact that the assumptions about the foundation were wrong. He assumed much sounder foundations than were actually present. Again, there's no record that I know of what calculations were done for the stability of the arch itself. Now we have Navier, whose main contribution is elastic analysis, but in the earlier editions of his teaching, his course notes for the École, covers arch theory. And he inverts what Culmann said and states the modern understanding that if the thrust lies between the limits, then the arch is stable. So if you can find one line of thrust that fits within the masonry, then the bridge will be safe. Grosvenor Bridge in Chester, it's George Rennie. His father, as IC president in 1846, credited George with doing the analysis for the bridge, equilibrating the bridge, and designing the centering. It's interesting that the latter is contested. The Trubshaw, a dependent of the contractor in building the bridge, presented a paper in which he makes a rather firm claim that the centering was both designed and constructed by his staff. The bridge was originally designed by Thomas Harrison. We don't know where Harrison's confidence came from. So here's someone planning to build a bridge which is bigger than any that had gone before, 200-foot span. Why did he think it was going to work? There's no record of how Rennie's equilibration was done, but it does include a typical Rennie family detail where the masonry has courses right down into the foundation that are intended to be normal to the thrust. The paper about this is lovely and well worth a read, the IC proceedings. There's a lot of finesse and handling of deformation during load transfer from the centering to the foundations. They had folding wedges under every single voussoir all the way around the center. And they were, as they removed them, they were measuring deformation and tuning where the load was taken out first. There were lead wedges, several inches thick at the intrados, at the springings, that would squash as the load came on and ensure that the bearing was across the full depth. And for the outer thirds at each side, a lead sheet at each joint at the intrados, again, just ensuring that you get full bearing without cracks opening. And it's reported that the crown only dropped 2.5 inches as a result of all this effort. That report is given to the nearest eighth of an inch, which is an interesting bit of surveying in the time, presumably with the water level. And no derangement of form was perceptible. All joints remained closed. And so why was Harrison so confident? So then we get to lines of thrust actually as understood now, which were independently discovered, developed, if you like, by Méry in France and Moseley. It's still known as the méthode de Méry in French. Huerta says that Moseley's was the first precise definition of the line of thrust. I'm not exactly sure what that precision is. He was one of few British contributors who'd read all of the French work, up to but not including Méry. And he explicitly linked his thrust line with Coulomb's theory of collapse. And he didn't do any experimental work himself, but he referred to lots of it work done by others. This again, this period is very interesting because these questions arise of who knows what. Brunel is very clearly calculating thrust by 1837. There's an interesting bit of subdivision of this mass of masonry over the pier going on. It's not quite clear what's happening there, and the lines drawn connecting 2 points on the upper part of this block to 1 point on the bottom don't make any real sense from a thrust point of view. But there's a clear procedure, and there's actually a design procedure visible in his notes about how you get from your starting point to a sound design. And again, Maidenhead had some difficulty, but it wasn't to do with arch stability. It was more likely to some combination of striking the center before the Roman cement had gone off, and some foundation issues. There's no indication of his thinking about soil structure interaction and how the thrust and the movement in the foundations works. There's a record from an article by Owen that he instructed his assistant, quite late though, that all forces should pass exactly through the center of any surfaces of resistance, especially in anything resembling a column or strut. And Owen suggests that an arch might be seen as resembling a column or strut, which is fair enough, but of course, he wasn't building arch bridges by 1854, so so we've got the state of play in the 1840s. Basic assumptions established: infinite compressive strength, no tensile strength, failure by hinging. We've got a line of thrust, a very mathematical presentation by Moseley, and the implications, exactly what the indeterminacy means. This line of thrust could be in lots of different positions. What are the implications of that? Are not necessarily clear, and this is where Barlow comes in. And this, interestingly, doesn't particularly feature in Haymann's presentation, but seems to me to be absolutely central. Barlow comes along to the ICE with a suite of physical models. John Rennie's in the chair, Brunel and Stevenson both in the audience. And the paper is comprehensive. So there's a visual proof through a suite of models, practical methods of actually constructing lines of thrust, and a deep understanding of the link between theory and real structures. Both the paper and the discussion are well worth reading. The discussion is hilarious. Mr. Bidder was tempted to consider an arch constructed of rectangular bricks set in a matrix of cement as a bent truss girder, the tension rods of which were represented by the abutments of the arch. Very flat arches, such as Maidenhead, were examples of what he meant. Mr. Brunel could not agree with Mr. Bidder's comparison, or what he might be permitted to term his amusing theory. The dripping condescension. Mr. Bidder was right, I think. It's not an unreasonable analogy. So Barlow has this sort of mostly graphical. There's a bit of calculation and there's the ratio of these lines, but a mostly graphical method for constructing lines of thrust. But the most significant thing is all the discussion of what it actually means. So he identifies that the maximum horizontal thrust is the resistance that the arch can give if the abutments push, and the minimum is the force that can be exerted by the arch on the abutments. And that's the first time that has really been explicitly drawn out. He identifies that if you've got arches meeting at a pier, the different geometries, then the relationship between these maximum and minimum are really important. Your minimum at one and the maximum at the other become relevant. He identifies that just because your masonry is built to a particular springing point doesn't mean that that's the structural springing point. And draws attention to the complexity of real structures in comparison to a 2D arch. After that, there's multiple rediscoveries, lots of discussion. What becomes known in more recent times as the safe theorem gets into standard text, and people start using it as a routine thing. just accepting that if we can draw a line of thrust within the masonry, then it's sound. And graphic statics, these lines of thrust and the funicular polygon get refined into a much more comprehensive system. But fitting a line of thrust is a really laborious process. It's still in use right through into the 1970s. You got your funicular polygon there, but this point has to be moved about and the line redrawn by iteration to make it fit. So you're talking about several hours of work for one bridge, one set of loads to go through that process. Obviously, the more you do it, the fewer iterations you have to do because you get a feel for what's going on. Okay, that's most of the theory in place. How did we actually test what's going on? Da Vinci, incredibly, has a set of drawings of tests on arches. It's not clear whether he actually did them or whether he thought about them, whether they were thought experiments. We've got the effect of an extra trip load in the collapse mode. Hope was an experimentalist. He was curator of experiments for the Royal Society, and there's the documentation of interactions where he was repeatedly promising experiments to prove his theory. Unfortunately, there's no record of the experiments that were done. I note Bill wrote a New Scientist article many years ago, in which he makes specific claims about what those experiments included. I think he did that. But he was a practicing engineering experimentalist, and he certainly would have been thinking about finite pieces and interactions. Gautier in 1717 built timber voussoirs, semicircular arch. He built this half arch setup with blocks on the back and took these off one by one and determined that it collapsed when he got to point 11. If you do the calculations, it should be fine without them at all. So that obviously he encountered the problem of physical experiments, that if your model isn't perfect, then results aren't either. We've met Danisi before. An extraordinary collection of experiments presented to a public meeting, so might have been known about. Only one plate published in 1732, a bit more detail in 1739, but in a very obscure journal. But he very clearly demonstrated that arches are failing by hinging, not sliding in general. Much concern about the dome of St. Peter's in 1748, and as a result of that, physical hanging chain models are built as part of the process of proving that it is safe, and also of estimating suitable forces to base the design of a hoop at the bottom on. In 1774, we've now got Perronnet starting to produce very long span, low rise bridges with much higher abutment thrust. And his contractor built a series of models for one of his early bridges. And he interestingly identified that sliding failure in the abutment was a real risk for those under dead load. Another set in 1810. There was nothing particularly new in Weisstad's experiment, but they were sufficient to convince engineers at that point that the no friction model was wrong. And Rondelet claims to have made an infinity of experiments using 54 models of volts of different forms and different extras. Probably the largest set that has ever been made and that ever will be made. But he was trying to produce new rules of thumb. So he was doing this thing where he was doing lots of experiments and producing data and then trying to fit a new rule of thumb to it. So the old approach, just based on his experiments rather than by observation of previous successes. And we come back to Thomas Harrison and Grosvenor Bridge. This model is currently built into the embankment on a slightly obscure side street near Grosvenor Bridge in Chester. It's Thomas Harrison's model. The question arises of whether it's purely an architectural model or whether there's some intention of structural interest. We see the spandrel wall is a solid piece, rather cracked. But the soffit is individual blocks and the ring base. So it's not inconceivable that that was actually intended as a demonstration of stability. He did his own experiments as well, quite large span. And Barlow, of course, the whole thing about Barlow's paper was that it involved all these physical models. So he introduced the wobbly arch, which becomes a stock in trade of the educator, which beautifully shows how, as you load the top, although the arch goes down, it goes up. And that interaction between thrust and deflection. Just as an aside, Fleming-Jenkin illustrates in his article models very much on the same basis. But the key model, the key observation is that you have these different, the fundamental model, most important model is this one. 6 voussoirs with wooden slips between. Each has 4 pieces of timber. So you can take them out in any combination and show one by one that the different thrust lines all work. Quick technical bit, just in case it's not familiar. What is thrust itself is just the resultant of stress at some slice through the arch. It's the force you need to maintain equilibrium if you cut the arch there. If you rotate the axes of these forces so that they're normal and parallel to the cut, then you've got a shear working along, and this is the thing that we're saying will never be enough to induce sliding, and we've got a normal force. Divide the moment by the normal force and you get an offset, which is where that resultant acts. And thrust is simply the locus of points as you do that for every section, for lots of sections around the arch. Relating to stress, if there's no tension, then the thrust is the centroid of a compressive stress distribution. The actual stress is unknowable. But if you assume linear stress, it gives you some kind of idea of what's going on. And this picture at the bottom shows a line of thrust running from outside the third point at one side to outside the third point at the other, and you can see how the stress varies. Where the stress goes to 0, a crack opens. If the stress balances, then they close again. If that line of thrust gets to the very edge, then it means the stress is infinite. It implies the stress is infinite. So if the line of thrust is at or beyond the edge, that's an impossible state. You have a simple arch built on centering. The arch sags when you take the centering away, pushes on the abutments. And if it goes far enough, you get those cracks opening. These ones might not be exactly at the springing. That one would only be central if everything is perfectly symmetrical. And obviously the thrust can't pass through the crack, so it has to go from this point to the crown, extra loss, and down to this point. If the abutments push in, the arch will squeeze up. And you get, again, has to go through the points of contact. So it has to be much flatter. And those are exactly Barlow's limiting lines. Need not be symmetrical. This is Bill's model, showing the thrust going from extrados at one end to intrados at the other. That, of course, means that your equal horizontal thrust is not aligned, so there's a moment, so there must be a different abutment vertical reaction to balance that moment. Is that a meaningful state? Sure. Both abutments tilt the same way. That's exactly what you get. And that model has a pair showing Hooke's observation. Works perfectly well, and even in this this is an inverted photo of a suspended form. The voussoirs take up the right angle. So the calculation is easy if we have 3 hinges. It's all simple statics. The 2 cases, your vertical offset is lower, your horizontal offset is bigger, so the horizontal component of thrust increases. And in between, we've got no way of knowing where the thrust acts on the crown and springing in a particular case. But if we choose values for the unknowns, we can calculate the implied thrust from that. And that's exactly what Young were doing. They were saying we're going to fix the thrust at the crown in the middle and somewhere down here in the middle, and we're going to try and find a form for the bridge which keeps it near the middle through the whole thing. Brunel was doing it as a design, Young was doing it as a test of an existing bridge. In terms of understanding how arches behave in situ, the passive-active interaction is really absolutely fundamental. So the arch has a passive-active behavior in the same way as the soil. If you push on soil, it pushes back harder. If you move away, it pushes less hard. The arch does the opposite. And so they can find equilibrium. But they have to find equilibrium, and finding it involves movement. Small movements, but significant movements. If you find that the minimum and maximum don't work out together, if the minimum arch thrust is greater than the maximum available soil pressure, the arch will keep dropping. It's not particularly common, but it does happen. And if the minimum soil pressure is greater than the maximum arch thrust, then the arch will burst upwards. And that, again, is rare, but it does happen. Here, there's a big hill up the side. There's a huge shallow slip bearing down on that abutment, squeezing the arch. And this one will be familiar to some in the room. And the span of this arch has gone down by about half a foot, or round has burst upwards. I'll skip through those. The medieval tradition had been, the Mason secrets were rules of proportion. Thickness of abutment relative to the span of the arch, and things like that. And they were expected to work at any scale. You can build a model this big, or a cathedral, and the same rules work. Strength of material just doesn't feature. And interestingly, arch theory, as developed through to Culmann and Barlow, also doesn't mention that theory. Galileo challenged that, laid the foundation for strength of materials, introduces the square-cube law, and observes that if you double the length, your weight has gone up with the cube, but the available capacity has only gone up with the square. Just looking at some pictures from our Archie software, doubling every dimension as we go, but not the material is great. So the thickness of this line is how much of the material is needed to sustain the load. And you can see that thickness increasing. The general shape of the thrust isn't changing much. But as we double and double and double, eventually it doesn't fit at all. You're unlikely to build a 100-meter span bridge with a 5 megapascal brick. If we double the strength as well, then you can really see that there's absolutely no change in the form of the thrust. So as long as we are a long way from capacity, then the medieval rules work fine. Now they obviously introduced the ability to actually resolve indeterminacy by introducing elastic properties. And he defined the job of the structural engineer as calculating unique internal forces, deriving the internal stresses and comparing those with material strength, which Hamish introduced soon, called Navier's straitjacket. Barlow's paper Brunel in the discussion asked about elasticity. He said this is important. I didn't see you mention it. Yeah, he actually said I've endeavoured to find some points to pick. It's very difficult because his practical experience is just too great. And Barlow said, yes, sure, that is an issue. Basically, we deal with it by keeping the thrust well point away from the edge. So there's no suggestion we should try to analyze the elasticity. It's just we have to accept that the crown will drop. We need to allow for that. There's a lot in more recent work. The middle third rule comes up, and we try to keep the thrust within the middle third. Obviously, that implies that the arch could stand without any cracks opening if the thrust actually stayed in the middle third. But just because it could do that doesn't mean it will. So as soon as the thrust goes out of here, then your cracks start opening. It's a very conservative rule. What happened after Barlow? Basically, that was finally we had a pretty complete understanding, but we stopped building big masonry bridges. They carried on in France and Germany, and China carried on right through into the current century. Other types of arches, big arch bridges, non-masonry, were treated elastically. But you still can't get away from the impact of the assumptions you make about abutments, even if you have a material that can sustain tension. And small masonry spans continue to be built by the thousand without any use of theory. The experiments continue. 1895, the Austrians set to prove the validity of the elastic approach, building enormous models, 23 meters span in brick and stone, mass concrete, reinforced concrete, steel. But they set out with the specific aim of proving elastic theory. And even when their data showed that the behavior had gone beyond elastic, that was ignored. 1919, Castigliano comes along with an economical method of solving the elastic problem, and also shows a way of analyzing masonry bridges by saying, well, if we have a masonry arch, we do one elastic analysis where it shows tension, we then take that material out, we keep the weight, but we don't allow for the material to be used in the analysis, and we iterate, and we quite quickly converge on a solution. But all of that work gives you stresses for particular foundation behavior, as presented for rigid foundations, which isn't what you would tend to find. But nonetheless, obviously, the elastic methods were very widely adopted outside arch analysis. And now we've got the question of live load. So 1876, Fleming-Jenkin in his Britannica article says masonry arch differs from the superstructure of other bridges in that its dead load is so much that we can ignore live loads. You know, that's the new London Bridge. You can see that that live load is just not going to have any effect on the bridge at all. That starts to change, obviously, in the 20s, 30s, and particularly with the onset of war, where you've got tanks and tank transporters being moved around. The rail situation is a bit less obvious because locos get heavier sooner. But Pippard then takes this question up, and the issue of assessment of existing bridges for heavy loads becomes a thing. Pippard starts with another round of model experiments and develops an assessment method. His experiments don't add a lot, really. His first set used polished, very, very finely machined voussoirs, and one of his observations was that any lack of fit and your structure reduces to a three-pinned structure. He did another set then with concrete voussoirs and mortar. Pippard was convinced that the elastic analysis was the way to go, but he didn't have digital computers, the human ones. And elastic analysis of each individual bridge was even less viable than the graphic statics approach. So he sought to simplify it to something akin to a rule of thumb, essentially. That doesn't really generate any understanding. It's just a tool for deciding whether a bridge passes or not. That was further refined or modified by the military engineering experimental establishment in and post-war into the MEXI method, which is still used. There's a simple formula in terms of the span and the total height, including the ring thickness and fill at the top, for a provisional axle load, and then a series of factors that reduce it. That's for a parabolic arch. So you have a factor for shape and you have a factor for various factors for condition. And to make that even quicker, it was presented as a nomogram. So you've got the arch span and the total thickness, and you can draw a line through to get your provisional axle load, which is a lovely thing. So your military assessor could come along and get your read off the value in no time at all. But it didn't do everything, and graphic statics was still in use. When you're stopping loads and bridges, it gets complicated. If you're just thinking about dead load, you can take a 2D strip, and that's fine. As soon as you start putting a load on top, you've got patch loads in different places, and it gets really complicated. A skew bridge is even more complicated because they don't like the abundance. So we have to introduce rules about how things go. And according to the British rules now, loads distribute differently on road and rail bridges. And there's no distribution in the masonry at all. So once the load gets into the masonry, it's stuck in a little. So, 1930s, Jack Hayman, a young Jack Hayman, is working with Baker in Cambridge. It's found that measuring stresses on site in new steel buildings, the results don't bear any resemblance to the stresses calculated by the designers, which is obviously quite alarming. How do we know that our structure is safe if our analysis is wrong? So there's a big research program, very large scale models of steel frames tested to destruction. And that results in plastic theory and a new method for designing frames. And the core of that is this, which Hayman always presents in anthropomorphic terms, as if you can find a way for the structure to stand up, then it can find one too. The way it finds is probably not going to be the same as yours. And that was then applied to masonry rather later. Hayman is always very careful to credit the initial insight with someone else, but it was Hayman who did all the word spreading, did the developing, did the marketing, providing a theoretical basis to what Barlow had already presented and what many by that time had accepted intuitively. But plastic theory requires ductility, and masonry is a brittle material. And masonry structures are ductile. They can tolerate large deformations without collapse. In bending, by squeezing that mortar at the corner. The assumptions for plastic theory are exactly the assumptions that Culmann identified. Hayman produced from that a way of assessing masonry bridges, but no computers, involved drawing. It worked with a single axle load at the crown. And you have to deal with the fact that the load is narrower than the bridge, and he followed Pepard with an effective strip. And this is where I start to become aware of what's going on. This house was full of personal computer world magazines when I was a kid, and every edition had a new exciting British-made computer all competing for market. Adam eat the apple? No, it won't disappear without trace. And Bill had just started as a lecturer, having spent an early career building big steel bridges, needed a research topic, and Alan Vardy nudged him in the direction of arch bridges. And he saw pretty quickly that taking Hayman's approach and putting it onto a computer would be very powerful. So the first iteration was on a programmable calculator. You would just give you a question mark, and you would type in hinge positions using indexes of the positions around the ring, and it would spit out a thrust and whether the a horizontal component of truss and whether it fitted. The next version was on a NPL decision mate. It didn't come with the person who was always there on the adverts at that time. He demonstrated it. It was supposed to be a research presentation meeting. The Northern Ireland Department of Transport said, we need it now. How much do you want? And in various editions, has been in continuous use for 40 years or so, or nearly 40 years. And the two big innovations there, one is this just automatic search for a viable thrust and calculate and display, which means that the engineer can interact and see what the behavior means. And it took maybe 3 seconds to calculate one case on 1984 hardware. It's instant now. But also the zone of thrust. The zone of thrust deals with this business of finite strength. So we say, rather than a middle third or a middle half, we say, if we have a material strength, then we know that as we get towards the edge, this will start to flatten, and the limiting case is a uniform stress at the edge, at material strength. We get local crushing, so the area always increases to be just enough to carry the load. So that tells us how close the thrust can be, and because we can do the calculation at each section, we can tune that so that we never let the thrust get too close to the edge. And that's the zone that Archie draws in this. And the thing about Archie is it's supposed to be exploratory, so you can interact with it and see the implications of what you're doing. So here, for example, we can say we're not going to allow the thrust to go within, so say we've got lots of loss of mortar. We can just drag it up and see how that affects thrust as we go. But because we're running out of time, what about bridges? All of that has been about arches. Maybe back to the last couple of slides. That's an arch under thrust. That was the bridge. But before they got to that point, they had to remove parapets, spandrel walls, the road, the fill, the backing. All of those components have a significant impact. Pure 2D statics has real power. It allows you to demonstrate to people who really don't believe that it's possible, for example, that you can cut a bridge out of its abutments and jack it a meter up into the air and then fill in the gap. But even in 2D, there are real complications. And when masonry starts to get thick, things get weird. There's no change to the pigments. We start to thrust at a different place. In this case, it's close to the centroid and it's not too bad. Here we're running well inside and things get very odd. If you change the cut, change where the center of those radial lines is, then the apparent thrust will move. And clearly that's not physical. And once you get outside 2D, bridges get really, really complex. Materials have unknown properties. Genuinely unknown properties vary enormously in order of magnitude, in time and space, if they get wet. Across the bridge, the internal masonry is typically much less strong, much less stiff than the skin. Our distribution business, once that load gets into the ring, clearly it continues to distribute in just the way we're perfectly happy to say that if you put a load at the top of a wall, it doesn't go straight down and appear as a patch load at the same size at the bottom. That's what so that straight down behavior is what our rules of distribution say. And then viaducts. So Archie customers, as soon as they got Archie, they said, what about multiple spans? And Bill went to Barlow and this interaction, the passive active interaction of spans, and implemented that in multi, which is now part of Archie. But observation of actual behavior makes it clear that that's not the whole story. If you look how far from the springing, this is London Road in Brighton. The bomb took out one span, so 2 spans, 1 pier. But there's a huge amount of masonry up from the springing still in situ. Simple elastic model, no backing and with backing, shows just how profoundly that behavior changes. And that has, once you add the 3D components, the spandrel wall and parapet on top, has massive effects. Cracks start to open and close. Mud pumps out from the fill. You get crushing at the centers of rotation. You get all these kind of behaviors. Horizontal cracks across the ridge. Spandrel cracks are a very common defect. They can develop very slowly, but we tend to say the spandrel wall is not considered an assessment. That's fine, because it can only help. And if we break it off, then that means that our assessment isn't going to suddenly be wrong. But things can get really bad. And masonry like that falling out is a real problem for the people underneath. They can be hidden. This wall is walking out because a crack has come down the inside and stepped out to the end. So this will often be regarded, particularly if there isn't a big step, but often if we see a crack there, an open joint will say it's ring separation. Very often isn't. Does that mean we need complex 3D models? For assessment, really no. There are neither the resources nor the required input. The resource issue will no doubt get easier over time. What we can do now compared to what was possible with finite element analysis when Bill got started is night and day. But the data issue will never go away. We simply cannot have the data that would justify building a model like that of a particular bridge for an assessment. We need engineering models that are actually diagnostic, more like thrust models than like 3D FE. Just out of interest, this is data from a set of vertical deflection measurements. So that's the south quarter, crown, and north quarter of a bridge spanning this way. The deflection at the north quarter is very much smaller than deflection at the south, and that's consistent with traffic in either lane in either direction. So it's not to do with which way it's approaching, whether it's impacting on the bridge as it hits the rising curve. What can analysis make of that? The only way you'd even know that was happening is if you measure it. There's nothing on the bridge to suggest that there's an asymmetry or a possible cause for that. And measurement comes up with that. Every time you measure something, there's something like that, some difference of behavior that is to do with the unseen. Does that mean that detailed 3D models are no use? Equally emphatically, no. They allow experiments, in silico experiments, structures on hypothetical structures that would be uneconomical in the physical world, either to support the development of new understanding or to test designs and possible responses. And so my take on what's needed at this point is lots of detailed measurement of behavior, like produce the results in the last picture at service load under real loads on real bridges, and systematic numerical experiments using detailed discrete element, elastic plastic, finite element models that allow us to test hypotheses of behavior. But this bit is key. It's no more, so our experimenters that did an infinity of tests and wanted to derive rules from it. If you try and run big complex models and then derive general rules, it's exactly the same thing. You need to start with a hypothesis, build models to test it. So the stability of masonry arches 2D problem has been fully understood for a long time. So it had to be rediscovered repeatedly. It was forgotten at the start of the 20th century. Heyman brought it back in with a solid theoretical foundation. Bill Harvey obviously brought that into widespread use for assessment. One of the interesting things from my experience is that the interaction of interactivity with thrust allows you to develop an intuition about behavior if you understand what the computer is doing and can interact with it. But regarding the capacity of masonry bridges, it's a different and much more difficult problem. Zone of thrust is good enough for ultimate load tests. Safety against collapse, though, is very rarely the main concern. there's lots of conservatism in typical assessment. You usually run away from any kind of risk of collapse. But a bridge can be at no risk of collapse and yet suffer serious cumulative damage. Real masonry bridges are doing that all the time. The actual stresses are unknowable. So we can't just do some sort of complex analysis and get an answer. And there's still a vast amount to learn. Always welcome challenges, questions, interactions. And for those that don't already know, I haven't quite kept up with monthly since Bill died, but I'm trying to keep up Bill's Bridge of the Month newsletter.
Hamish, that was fantastic. Thank you very much indeed. Very good. Okay, we now open the meeting for questions. So would anybody in the room like to fire off a question?
Yes, please. Graham Slade, WSP. Very interested in the talk. Thank you very much. Also very interested in your comment about still building arches in China in the 21st century. What do you know of Chinese theories? Are there any?
I don't. I mean, I would assume that particularly the more recent ones, so the 21st century bridges would be using the same big design packages that people are. To be quite honest, I was slightly surprised to discover that they were still building actual masonry unreinforced bridges that recently, and I only discovered that very recently. So there are so many avenues of further research that came out of this process.
Do you know what sort of span the Chinese?
Big ones. So the reason the discovery was specifically in looking at the Wikipedia list of longest span masonry bridges, which basically just has a whole series of Chinese bridges over the last 100 years. So yeah, big things. And there was somewhere related to that, there was a question about whether they would still be doing it, because maybe it depends on low labor costs, and maybe that's changing in China too. I'm more interested from the new masonry bridges point of view in new small span bridges, reinvigorating it as a way of doing the many small bridges rather than a few big ones.
Yeah. Have you talked to John Ossendorf, the people who have been creating these interesting 3D incredible working from hybrids assumptions?
Not yet. No. It's a fairly. I'm also very conscious of the fact that there's a load of work that I haven't mentioned from the last 30, 40 years, 30 years post Bill start. Matthew Gilbert and Sheffield and Philip Block and John Ossendorf and people. The theory has been pushed. So the Ossendorf block stuff is just incredible.
Yes, John.
John Wood's various railway backgrounds to my now retired life. Are you working on viaducts at all, Hamish, and the sort of series of bridges and problems that poses?
We'll be careful about tenses. So right at the moment, not really. It's something I want to get back to. So we did a couple of years ago quite a big for us research project with Network Rail, which was trying to tackle this problem, saying to produce an evidence base on which to start building some new we can see that some viaducts on some loads are suffering serious damage, and some aren't. And we've got absolutely no basis on which to separate the ones that are from the ones that aren't. We can't go to a bridge and say this one's likely to cause trouble, that one's likely to. And the only way we can get to the point of having that is to collect the evidence. But it turns out, as I learned partly from the project, that evidence collection has to start much further back than I expected. So I knew we needed to get the deflection measurement, start looking at the actual real 3D behavior under load. What I hadn't anticipated was that we have no idea what the population of basic arch dimensions on the network is. We simply don't have a systematic record which spans rises, shapes.
Thanks.
Which is a hard place to start from.
Purely procedural, is your microphone on?
Is my microphone on, Mike?
Not sure.
I turned it on.
Remote means it's hearing.
It
is,
is.
yes.
It's on.
Okay.
Yeah, it's on. One thing that I was slightly surprised you said that Culmann's memoir on statics and so on. You weren't aware of a practical problem that he was trying to solve. Is that right? Or did I misunderstand that?
Did I say that in the context of Barlow?
No, no, talking about
Was it specifically
the introduction of Culmann, his essay. No, it's just
I'm not sure
that
what it is.
I always understood that he was trying to help the French military fortification effort. What's the name of the man who did the enormous fortresses at the end of the 17th century? Anyway, that he was trying to find ways of predicting the stability of retaining walls in military fortifications, and the associated problem of the arch thrusting against it or whatever.
Yeah,
I don't know whether it had any,
I'm not sure what I said. It's certainly not what I meant.
yeah, I'm not sure they had much effect on the practice.
Yeah,
I think that's correct.
The business of how these developments end up weaving through each other and into practice is really fascinating. We don't,
Yes.
and who picks up what,
Yeah.
how many times the same thing is rediscovered.
Yes.
Yeah.
I mean, Peter Barlow is another very interesting case, and he's been much neglected, I think, by historians of structural engineering. But for instance, he is reputed to have calculated the action of the Albert Hall roof, which is not a simple problem. The calculations are reported to be somewhere when you go to that reference, they're not there. So,
Yeah.
but he was a major contributor to the Royal Commission in the application of iron to railway structures of 1848 or 1849, and made some very interesting observations in there too. So I think he's well worth.
Yeah.
Well studied.
This is W.H. Barlow in this case, is it?
Oh, is it? No, I think it. Oh,
William Henry.
Then you've got Peter Barlow, Peter Barlow, and then you've got government, you have PW in the Senate.
so you
So W.H. is his son.
Don't-
Peter is W.H.'s father.
Yes, it is. There's Peter W. Barlow, who is
It's more bridge fame.
right.
He's
You know which part of it is the case.
yes, it is William Henry.
Oh, right.
The thing that's really striking about that is the fact that it's all there in that one presentation. That deep understanding of actual, real structures, and I mean Brunel's comments is just delightful. It's like I
Yeah,
was trying to find some way of getting in,
yeah.
and I just couldn't.
He wasn't good at collaboration.
That was all happening at a time that that was exactly contemporaneous with the main edge difficulties.
Yeah.
So the questions of whether this was relevant to the trouble that made would have been very clear in everyone's mind at that
Yes.
discussion.
And the contribution that Telford made, I think, part of it is really that he, from the collapse of bridges in a generation before him, he realised the vital importance of getting your foundations right. And so he paid much more attention to the design and stability of his abutments than previous generation. I'm trying to remember the name of the man who bridges kept on falling down in the years before. But anyway, it doesn't matter. Yeah, that was so. Telford really understood that arch foundation interaction problem in a way that I don't think previous engineers had.
No, and then that too is obviously a problem that becomes more significant in scale.
Yes.
The bigger and the flatter, which
Yes.
the more challenges you encounter.
Yeah, no, that's right. So,
Um,
Rob,
we had one question from the Zoom audience, from Bob Wright. Spandrel wall failures are a common failure mode, especially at the connection to the extrados. How was spandrel sized historically?
The answer is simple. I don't know. They're clearly intended to contain fill, so there's some obvious element of retaining wall to it. How much they were designed and how much they were rule thumped, I don't know. But those failures aren't because they were wrong. They are a new thing. They're happening because live loads have gone up. And they're driven by quite complex behavior to do with small movements under live load and camming of little bits of material in the gap as that cyclic movement happens. And that is absolutely central to the viaduct questions, the issue how to understand what drives that problem and what on earth to do about it. Sticking our heads in the sand and waiting is obviously the standard political mode. The railways are in a bad enough state if we have to replace 3/4 of the bridge stock. It's a pretty terrible situation.
Well, in railways.
And you had a photo of is it like a railway viaduct with the span collapse because of an explosion? Was it blue?
Oh yeah,
Yeah. See in the just above the piers, it looked as if there was like like diaphragm walls. Is that common for
Yes.
viaducts? What's especially when like your dead load, you want that to be so large that the live load is almost insignificant. Like, what's the reason for having voids like that?
So at the time these were built, it wouldn't have changed the fact that the dead load was still significant relative to the live loads of the time. It provides, they were typically, it's not obvious in that case, in that picture, whether that was the case, but they were typically directly under the rails as built. So you're putting the load straight on the wall. There would be solid backing partway foot width, and then walls have stable material. What all the rationale is, I'm not sure, but it's very common. And it's not even entirely restricted to viaducts, though they appear in cable span bridges as well. You get cellular abundance, get sort of all things going on for certain designers. One of the other things that Bill has been advocating for a long time is that we need to have a serious survey of the railway network by contract and design. So you can establish what to expect on any particular structure, even if you can't get a drawing, which you often can't. So you can say, I want to know about this bridge, and it'll actually spread out and say, what can we find that was designed by the same person, built by the same contractor? Because that will tell us what to expect. Complex cases of people saying, we find a void in this bridge, terrible excitement, fill it with concrete.
So it's not a simple matter of saving weight.
There might be some element of that, depending on the geometry, getting weight off the lunges.
Saving material.
Material surely is a significant thing.
This is the Brighton part. Yeah. So this is an age where bricks and labour are cheap. And so you can employ people to build more complex masonry rather than haul tons of chalk rubble or whatever. I don't know quite what the issue was there.
Yeah. Sometimes they jack up to the top, sometimes they just have slabs over the top. Sometimes those slabs break and ballast starts disappearing in. Because what happens on the railway when ballast starts disappearing? And the fact that it's on a bridge, nobody stops to think about. Where's he going?
Yeah. David.
I'm one of those people present who's not an engineer, so I want to thank you for explaining that so well to us who know a bit about engineering, but not everything, not all the terms. I want to go off to one side a little bit. I'm an architect and I look at cathedrals and all kinds of buildings. I'm wondering what your work can tell me about flying buttresses, which are sort of half arches.
So Hammond's work. There was quite a lot on flying buttresses, and they are, in a sense, less complex than masonry bridges. They tend to be more. They fit the model better in some ways. There are complications as ever, but it is a technique that's been used many times over many decades, hundreds of years, even to both post-Hammond with the explicit understanding of theoretical foundation and before tracing thrust through abundance and showing that they provide the necessary support for the main bolt. Is definitely a thing. It gets interesting. Bill did some work with Margaret, integral for wells, where there are flying buttresses coming off the roof and down through the roof space over the choir. And in the upper space, there's a big chunky masonry flying buttresses, and then they sit eccentrically on top of these skinny little columns in the choir, and cause ongoing mild consternation.
Yes, I think I remember Bill presenting a diagram showing that the chances are the thrust was ending up in a really small section of masonry by the time it got down to the column.
The model that Bill built, something that I would really like to get back to doing is 3D thrust calculation using horizontal slices through the. So just taking slices in each section, tracing thrust down through that, in seeing how it tracks in both directions, land in the right place. So there are all sorts of interesting things which can be done.
I think part of the answer about flying buttresses is that the dead load is well, the imposed load, which is mostly wind load, is generally relatively small compared to the self weight. So if you can establish a stable buttress, it'll probably stay stable. But also because of their proportion of height to base width, the problem with foundation stability and foundation rotation is quite serious. And I can't remember, is it Beauvais, which collapsed a few years after construction. I think Jacques' theory was that that was because of foundation movement. I can't remember.
Don't have it to hand.
No. Yeah. So, as you and I have both seen, when you build a buttress against a wall to stop it tilting, very often the buttress then tilts further than the wall because you haven't sorted out its foundations and connected it properly to the wall. Thank you. Yeah, please.
No, just general fan from BGNE. No, just talking about the window loads. My question is coming from my background from Italy. So, I mean, what about the seismic loads on recharges? I mean, the conservation of the bridge seems, you know, they do quite a good work. Even in Italy or any country, there are seismic effects. So, I mean, there is a way, I suppose, that we can consider seismic effects as well on the model.
Yeah, and they're just accelerations. So you can include the load that results from that acceleration and look at it. It's not something I've done. It's not something that's been demanded here. Clearly, it's interesting. There are other things that need to come into the Archie stuff in particular, like buoyancy from flood. It raises interesting questions. So other sources of load and seismic loads essentially just come under that category. You can introduce those loads and see what effect it has on thrust, see whether it can still support it. Whether you can the truly dynamic effects when they start rattling backwards and forwards get more complicated. So you can show that under any given acceleration it will induce the collapse.
So is the Italian experience that on the whole they survive earthquakes arch bridges survive earthquakes fairly well?
It seems that the new bridges, they don't, they fail, but the historical arch bridges, they still there. So,
Yeah.
So it seems the conservation of the bridge arch, they do much better than the new construction. So.
But one of those bridges of the month some time ago was a little tour of Christchurch after the earthquake. The bridges are out there, and there was serious damage. But you often end up with a situation where the bridge is clearly quite compromised, but still standing. In the same way as when a pier of a viaduct goes down by 100 millimeters, like the picture I showed, and the permanent way people come along. Fill in the hole, and the railway carries on running.
My limited observation from another earthquake zone in Jamaica is that if the earthquake results in bodily shaking of the masonry arch, it has a really quite good chance of survival. But if one side moves horizontally relative to the other, but obviously the span.
If they will apart, yes,
Yeah.
there is a chance that they will collapse.
The damage then the damage is much more severe. Yeah. Please.
Patrick Palmer, retired. I was with Professor Heyman when we had a structurals visit to Lancing College Chapel, which has flying buttresses, and we observed that there was a shear failure between flying buttress and the vertical wall it was propping. Coincidentally, we also discovered that the person who built that chapel wanted to have a go at the brickwork himself, and that was the joint which he did, and he hadn't put in the shear key. It just looked okay. From a masonry point of view, it looked like a complete thing, but obviously hadn't made the bricks go through into the wall.
I see, so it had actually sheared on the vertical
Yes.
joint.
And that makes
So it
me
wasn't
think
the-
that most people talking about flying buttresses concentrate on the two-dimensional effect of the vertical loads and where the line of thrust is. But it showed me that those flying buttresses also have a role in wind load, even though, as you say, it's a relatively small proportion. The joint was badly made and it showed up in that storm of, what was it, 57 or something.
Yeah, by the time you get to some of the more extreme Gothic cathedrals, particularly in Germany, with those very tall pitched roofs, the wind loads aren't necessarily that small compared to the self-weight. So you know, there is obviously a limit to how far you can go. But my impression is that certainly for earlier churches, that assumption that the wind loads aren't going to cause a critical state seems to be okay.
Can I just add to the picture on there, Brighton? It was originally constructed with lime mortar. When they replaced the viaduct, they used Portland cement mortar. And the people in Argyle Road, which is, you can just see at the bottom there, complained about the excessive noise.
Well, I wouldn't mind betting there's some quite sizable cracks between the bits rebuilt with cement mortar and the earlier bits with lime.
Yeah.
Completely incompatible.
One of the really interesting observations there is the fact that it's still standing. That there is a substantial crack on the far side of that pier, so it has moved. It's probably relying on the tension in the track to provide just enough to keep it there.
Yes, I remember somebody doing an analysis.
It's slightly complicated by the fact that at that point, the railway is curved in plan.
Well, you can see the rest of it going on around there, can't you?
Yeah.
Okay, and what question is, please?
Might be a bit of a general question, but what sort of repair methods, when you see cracks in bridges, would you recommend, and which ones you wouldn't recommend?
The first thing is to diagnose, and that's the step that's always missed. So there's we have standard repair details in the railway notebook to say you got a crack, you do this. Why is the crack there? Because if your crack is driven by this kind of movement, as often the spandrel crack is, then cutting slots and putting in 6mm heavy bars isn't very useful. And putting in cross stitching with thicker bars isn't either. It's going to be if you're lucky, you'll run the railway over before the water's gone off, and they'll just make a nice little pocket and move around in so they can't cause any damage. But yeah, so it's all about diagnosis and planning, and that's the thing that's missing. That's your question.
I said it was a general question.
You see time and time again that losses from the introduce of an arch are patched up and stitched in without, so that it looks all right. What it probably means is that next time a chunk falls out, it's going to be a bigger chunk. It may take longer to fall out. So
yeah, it's really alarming in some places where just over and over again the same patch gets put back in. So just gives it another chance to kill us.
Okay. Well, I think we did give you a run around page. Thank you very much indeed.